Here we want to look at manus variation in vertebrates. And recall that the word manus is the Latin word for hand. And so in order not to be too human-centric, we use the Latin term to be more general about this conversation. We want to start with the modern amphibian. And what we notice are 4 digits instead of 5. And Roman numeral 1, if you look at your own hand, is referring to the thumb. So, and your thumb is on the radius side. So if you see here, you have the radius, and that is the number 1 digit right there. And so 2 is going to be like your index. 3 is going to be similar to your middle finger, 4 ring, and 5, which is missing in this case, is going to be the pinky. So how do we know that modern amphibians have lost the fifth? That is because of the fossil record. We can see fossils changing over time where these digits do get smaller and the organism changes over the millennia. So modern amphibians, frogs, salamanders only have 4 digits. Now, when we look at the lizard, on the other hand, the lizard has kept all 5. Lizards are reptiles. So what we see are 1, 2, 3, 4, and 5 present. And also in turtles, we see all 5 digits, 1, 2, 3, 4, and 5 present as well. We want to also look at some vertebrates that have gone extinct as examples here. So the ichthyosaur, if you recall, is a reptile that looked very much like a dolphin. Reptiles did return to water and recolonize the water and changed their anatomy in order to do so, in order to be able to swim again. Dolphins and whales are mammalian examples for more modern times. And what we see is that the ichthyosaur had to change its anatomy in order to basically make a paddle-like flipper. And so see here the humerus, you still have the radius right there and the ulna. And it looks like the other bones kind of broke up into these pebble or rock-shaped bones that cluster around each other in order to make the shape of a paddle, because clearly this is a swimming appendage. And so that's how the ichthyosaur was able to do it. Now birds, because they have to figure out flight, they change their manus anatomy in order to make the wing. And so what we see is that we see fusions of 4-limb elements in birds. And we see basically digits 2, 3, and 4 that remain as these distinct bones. And these kind of, especially in more modern birds, will kind of stack up on top of each other in order to basically extend that manus out so that it can shape the wing for flight. And so these phalanges being very, very specifically adapted for flight. Now, the next thing we want to look at is what we call ungulates. And the word ungulate means nail, or an animal that walks on its nails. These are what we refer to as hooves. So there are 2 classes of ungulates. One is the odd-toed ungulate, or known as the perissodactyl, which just means odd number of toes, dactyl meaning toe. And the examples here would be the donkey or the horse or the zebra or the rhinos. And here you can see it in this picture with this one hoof right there. And that is basically the nail, and that's basically 1 digit. Now, when we look at the fossil record, and this is an ancient perissodactyl, so this is one that has not lost all the digits yet, but is in the process of losing them. And so what we see is that digit 1, digit 2, 4, and 5 are moving away from the ground and getting smaller and smaller. On the other hand, digit 3 takes over as the point of contact with the ground and also increases in size. What we're doing here is we're making the very end of the limb much lighter because these animals have to adapt to their predators by being fast. So they want to gain speed as their predators get faster. These animals also have to get faster, so they increase their speed by extending this manus and also getting rid of digits. A similar thing that we see is another line of this, which is the artiodactyls, or the even-toed ungulates. And these are your pigs, your goats, your camels, your giraffes, your sheep, your cows. So there are more examples of the artiodactyls. But basically what you see here are two sets of hooves, right? Basically, you can think about them as two nails. So these are even-toed ungulates, right? Because 2 is an even number, 1 is an odd number. Here, what we're going to look at is the pes variation. And remember, the word pes means foot in Latin. So again, we're trying to be more general when we talk about these, and so we use a Latin term. Let's start again with the modern amphibian. And what you notice in the modern amphibian is, again, a very similar anatomy as with their manus, where you have 1, 2, 3, and 4 right there, but you're missing 5. With the modern day lizard, again, very similar to their manus, where you have 1, 2, 3, 4, and 5 right there. And what you need to think about is, okay, why is it that modern amphibians and lizards have a very similar manus and pes anatomy? Well, it's because the manus and the pes for those organisms are very similar in function. They're doing the same thing, right? These are quadrupeds. They're walking on 4 limbs. Those 4 limbs are all pretty similar to each other. Obviously, there's going to be forelimbs and hind limbs, but they're similar in their function, right? They're stepping on the ground in order to locomote. When we look at a chicken, though, which is a bird, what we see is a very different pes anatomy compared to its manus. And that's because, right, the chicken is standing with its pes, but it's flying with its manus. And so here what we see is that we have digits 1, 2, 3, and 4. And so we've kept 4 in the manus. We kept 3 of them, if you recall. And this is in order to spread out the weight of the animal as it can walk. You can see that these digits are kind of pointing in these different directions in order to give stability to this animal as it stands. Here we see a fossil horse. And again, what we see is that the 3rd digit is going to become larger as the other digits kind of atrophy and become smaller. And compare that to a modern horse where basically you can barely tell that there were those digits in the first place. They are so small now and way, way up high above the ground. We do refer to the large 3rd digit as this very prominent 3rd, what we call the cannon bone. It looks like a cannon, I guess. But you can see again that this digit has become much thicker and is going to extend the leg of the animal, make the animal's leg basically longer, which will increase its speed, but also the limb will be very lightweight at the end because it's only 1 digit, and so that ends up becoming lighter than having 5. If we look at a cat, what we notice is that the rear paw, which is what we're looking at here, has 4 digits. What we did not see in the previous slide, but to keep in mind, is that the front paw does have 5. And so here, notice that we have digits 2, 3, 4, and 5 in the hind or the rear paw pes. And the human right here with its walking ability on 2 limbs, famous for walking. That's one thing that humans are good at, is walking on 2 limbs. And so this pes is clearly uh, adapted to that. And so what you see is that the digits all pointing in that forward direction, allowing for us to basically be very efficient in that direction as we locomote. We want to remind ourselves about the changes that took place as um, we colonized the land as vertebrates from the water. So, fish in general have a much more robust pectoral girdle. And the way to think about this is that their caudal fin, which is the thing that's most uh, in the back, which is where the propulsion has to take place, right? If you're moving forward, um, a lot of the propulsion to move forward has to be coming from the back. And so they have a caudal fin, which is obviously very strong and is gonna allow for them to swim in the forward direction. Um, and the pelvic fins, on the other hand, are much more for balancing out all the turbulence that can be in the water and for realigning themselves and to avoid the pitch and the yaw and the roll. The pectoral girdle, on the other hand, is also very robust, and that gives them a lot of swimming power. Now, what happens when we colonize the land is that the robustness flips to the pelvic girdle. So when you look at terrestrial vertebrates, and there's a common theme that we refer to, we see that the pelvic girdle becomes the more robust girdle. And you can think about examples such as yourselves as humans or T. rex. In both cases, those are going to be bipedal organisms. But also in a quadruped, what you see is much more robustness in the pelvic girdle. And if you think about it, the pelvic girdle is what is more in the back. And that has to give the propulsion in the forward direction, right? You need to have that engine in the back that moves you forward. So even a quadruped is going to have a more robust pelvic girdle. So what are the implications for this in terms of the build? Well, just notice here when we look at this picture of the pelvic girdle first in a terrestrial vertebrate, what we see is you see the sacrum, which is made of bone. You see the pelvis, which is made of bone, and then you have uh, this femur that attaches right to the pelvis in a ball and socket joint. And so that's a very, very robust structure of bone. Let's compare that to just a generic pectoral girdle. And what you see here is that you've got this scapula, and you have a scapula. So think about your scapula and how it's built, right? What is it attached to exactly, right? The scapula is very, very mobile on a human body. It can move a lot. And in the back, it's not really attached to anything that's bony. On the other hand, it does have a lot of muscle that holds it in place, tendons, ligaments, and so forth. And so this line right here is depicting that soft tissue that's basically attaching the scapula, right, to the uh, to the trunk of the animal. And so here is the rib cage coming out, which then, of course, is attached to the spine in the back. Now, this part right here, therefore, that soft tissue attachment of the scapula means that it's much less robust than the bony attachments that you see in the pelvic girdle. Now, the implications for this are less power. So clearly, right? Just take yourselves as examples. Your legs are much more powerful than your arms are, right? Everybody has some intuition of that. On the other hand, that soft tissue attachment gives a lot more flexibility, right? So you can move your arms around much more easily in many more directions than you can move your legs around. You have much less mobility in your legs than in your arms, much less flexibility in your legs than in your arms. Um, in terms of, if you want to think about clinical human medicine, which joint gets dislocated more commonly? It's going to be the shoulder joint versus the hip joint. And that's because of this much less robust attachment. Let's look at some vocabulary terms for locomotion. So, terrestrial vertebrates have figured this out in different ways. The term cursorial means running, and so an organism that moves about by running, we call it cursorial. So zebras and cats are cursorial, but here's an ostrich looking very happy, running about, not a bird of flight, yet a bird that can run. Some organisms prefer to jump around, and that's known as saltatorial. And so your kangaroo is an example of a saltatorial organism. Some organisms are able to dig and burrow and go into the earth, and we use the term fossorial for that. And just like the word fossil, right, means under the ground, the term fossorial means under the ground as well. So think about a mole, for example, being fossorial. Some organisms prefer to stay in the trees, and we call that arboreal. So a koala bear is an arboreal organism. Monkeys are arboreal organisms as well. Now, we use the term scansorial for organisms who don't spend most of the time in the trees, but can go to the tree for certain things, for getting food, or in this case, for taking a nap, right? So your jaguars, for example, can go up into the trees very, very easily. They can climb up there, but they're not going to spend most of their time up there. So we use the term scansorial for that in order to distinguish it from arboreal, because in arboreal cases they're spending most of their time in the trees, right? That's where they're most comfortable. And then taken to the skies, that would be aerial. So birds of flight and bats, those are aerial organisms. Now, what's particularly interesting are the mammals that recolonized the water. They had to do it in a very similar way as the reptiles that did it millions of years ago. We talked about the ichthyosaur having done that and having a similar anatomy to modern day dolphins. And so we need to be able to do it. Now, notice that when we look at a whale, the whale has lost its uh, the extensiveness of their hind limbs, and basically it's just this presence of pelvic bones that are still there, right? You can still see it right there. Those are the pelvic bones of the whale, but much more reduced. Now, this is because, of course, this whale used to walk about, right? Used to be a cursorial animal, but as it colonized the water, those hind limbs became less important. Just like when we talked about fish having a much less robust pelvic girdle, we see that the same thing happens again. And instead, what we see is that this caudal tail develops, and this caudal tail in the whale is these caudal vertebrae that extend down, and the undulations are going to be in the up and down direction, and so that the blade of these caudal tails will be horizontal, right? And so if you remember, the blades of the caudal tail in fish were vertical because the undulations of the vertebral column were much more side to side. And this is, of course, because, when you think about how worms squiggle about and how fish, you look at amphioxus and acorn worms and that type of movement, you can see how fish with their side-to-side undulations had to develop a vertical tail. But as we become terrestrial, it's much more about the spine uh, moving in the up and down direction. And you can kind of see that in yourselves as you can kind of curve your back into fetal position and then hyperextend it out. That's what is most natural for you to do. So it's interesting that both the ichthyosaur and which are reptilian colonizers of water, and these mammalian colonizers of water uh, change their anatomies in very, very similar ways. Now, that's not the only way to do it. It doesn't. It's not necessarily only with the vertebrae that you can do this. So notice that we do have a class called pinnipeds that figure this out in a different way. The walrus being a famous example of this, where these pinnipeds clasp their hind limbs together, forming a kind of tail. So on the outside, it looks very, very similar, right? It looks, if you didn't know any better, you may think that it would be built internally in a very, very similar way to a whale or a dolphin tail. But then when you look at the skeleton itself, you can see how different this is, right? That is the pes, right? The two pes that are sticking together in the back, and they are forming that horizontal blade. The vertebral undulations will still be in the up and down direction because, of course, a walrus is also a mammal, so stemming from that same similar terrestrial lineage that had to recolonize the water, we're going to see a similar way of figuring out the same problem. But it's interesting that the internal anatomy is different. So there are different ways that nature does figure this stuff out. So the next thing we want to look at is going to be how the limbs of swimming birds does change. And so um, we want to look at birds of flight, and we want to look at swimming birds. And there's everything in between, right? And so you can take a herring, for example, with a very, very light uh, structured upper limb. And if you're flying, you need to be light. And so what you see is this lightness of the bones in a lot of birds, in most birds, right? Because of the flight that they have to deal with. So they lighten their load. As we change to become more swimmers, right? And so we do see birds that are able to do this. Seagulls are a great example of this kind of maybe a transitional type of animal. But penguins are, of course, the most famous. And penguins being not birds of flight, can't fly at all, but can swim very, very well. And what do we notice? Well, we notice that again, we need to change this anatomy in order for that anatomy to become good for swimming rather than flying. So it's not about being light anymore. It's about being able to push the water. And there's a lot of resistance in the water. And so, because of all that resistance, these bones, and you can see how thick they get, right? They keep a very similar anatomy to the birds of flight, but that thickness of the bone is from all that resistance in the water. So that's what we're looking at with the pes. Now, I'm sorry, with the manus. Now, with the pes, what we're looking at is the webbing that we see on a lot of birds that can swim pretty well. So this is a blue-footed booby, one of the funnier birds that I think are interesting. And this bird, if you want to look at some YouTube videos of it, they are rather entertaining just to watch. But they are famous for being able to fly, but also diving to go and basically catch their food. They feed on fish, sardines, anchovies, yummy. And so, of course, they also need to be able not only to fly, but also to swim. And so what you see is that their anatomy is good for both. kind of an in-between anatomy there. Let's look at some vocabulary terms for locomotion. So the term gait refers to the pattern of footfalls. So every animal that we look at here for the rest of the lecture is going to have different gaits, and so we want to see how they use their limbs for locomotion. So these are just general terms for all vertebrates. A cycle is one complete use of all the limbs. A duty factor tells you the percent of the total cycle that the foot is in contact with the substrate. Okay, how can we make sense of this? Well, when you're walking, when we say walk, which is a slower locomotion, clearly 50% or more of the time your feet are in contact with the substrate, or in other words, the ground. Okay? And when we say, well, run, meaning faster, we think of it as faster, but the definition is actually more specific than that. It's when less than 50% of the time your feet are in contact with the ground. That means if less than 50% of the time your feet are in contact with the ground during a run, that means that for some of the time, neither of your feet will be touching the ground, right? So if you were to do a slow motion camera of a human running, let's say, you would see that clearly more than 50% of the time, neither of the feet would be touching the ground. And that gives us a term known as the suspension phase, which is the phase of when all the feet are not in contact with the substrate. And these are just some general terms. What we want to look at now is how do we become terrestrial? How do we go from fish to amphibians? And what were the difficulties of locomotion from basically having fins to then having these limbs that were used for walking? And what we think is that the early gaits clearly had inefficiencies. Early gaits meaning the movements that these colonizers on land were doing were inefficient because the anatomy was not really built for land at the time. It was still a very aquatic type of anatomy. So these are just some drawings of what kind of inefficiencies uh, likely arose. And so in this case, what you see is that this dot right here is the center of mass of that animal. And the center of mass, you always want it to be supported. So now imagine that this animal extends this forelimb forward and keeps the other three limbs basically where they are. When it does so, it's going to plant with this limb and plant with this one and that one as well, putting its weight on those three. And if we were to draw a triangle between those 3 points, what we would see is that the center of mass is outside of that triangle, giving that animal an instability, right? So this limb right here, what is it doing? It's lifting and trying to move as well forward. But that instability that you see there is because the center of mass is outside of the triangle. Okay, so that's when you're trying to move one forelimb on one side, right, and then followed by the hind limb on the other side. This would prove to be an unstable type of movement. So what if you planted on a diagonal the forelimb on one side and the hind limb on the other side, and you put your weight there on those two, and you drew a straight line through those as you lifted the other two limbs up, then the center of mass would still be off of that line. And so it's not going through that line, which means, again, there's going to be some instability. In order to fix this, what we see is that the tail can serve as a point of contact. And so that what we call is using a tripodal mechanism or a third foot there in order to basically create a triangle between this limb right here, that limb right there, and then the tail being a third point of contact while lifting this one and this one. Now we have a triangle between those points, and that center of mass is right in the middle of that triangle, giving that animal stability, that center of mass being right in the middle of that. And so now we have a stable movement. And without the tail, we can also try to gain this 3-point lateral sequence. And the lateral sequence basically means that the forelimb on one side and the hind limb on the other side move in the forward direction and are synchronized together. You're planting on the hind limb of the other side right there. And then as you lift that forelimb on that side, now you have this 3-point stability again, right? You don't need the tail in this case because you still have those 3 points. But those 3 points are spread out in such a way that the center of mass is now once again found inside that triangle, and you have a stable locomotion. So just compare that picture to the first one that we saw, where the triangle was off to off the center of mass right there, not allowing for that stability. So the most common way of locomotion for salamanders, for example, is going to be this lateral sequence cycle, which gives the animal the most stability possible. The limb is going to have to kind of roll about on kind of a circular motion because these limbs are sprawled out to the side. They're going to have to kind of roll about to get there. So it does not have the efficiency that we see when we get to dinosaurs, for example, when the limbs go right under their bodies. But we do see this very successful lateral sequence cycle. So that when you look at this picture in time, you see that this forelimb right here is lifted, which means that the balance is here on this hind limb, and that forelimb, and you can see this line kind of going down the middle there between that hind limb and that forelimb, the center of mass being in the middle. The next thing that happens is that this forelimb that was in the air now plants forward and puts weight on the substrate. At the same time, the opposite hind limb lifts. So now you have a new triangle that forms, and that puts the center of mass again still in the center of the triangle. That hind limb that was in the air now plants, and when it plants, it allows for the next forelimb on the other side to lift, creating another triangle again. And we repeat, and we get to the first picture again that we started with, and we repeat that gait all over again, or that cycle all over again. Here we can see a salamander moving with these lateral undulations. And so what you want to imagine are those triangles that we just referred to forming every single time the new limb plants. It creates a new triangle, allowing for one of the four to lift, and that keeps the center of mass of the salamander within that triangle. want to compare the limb anatomy of early tetrapods with their sprawled out stance compared to, let's say, eutherian mammals. And so we want to look at this salamander here, and what we see, and this is from the fish ancestry, right? With the pectoral and the pelvic fins kind of sticking out to the side for swimming. And what we see is that this amphibian here has kept that direction of these limbs moving out to the side. So the implications for this are that, as we saw in the video, the limb has to kind of roll over as it steps forward. That's not a very efficient movement. Also, the um, the limbs are far away from the center of mass right here, so that even that part is requires a lot more energy than having the limbs closer to you. If you want to prove this to yourself, just see if you can uh, put your hands on the floor, let's say, pretending that you are a salamander, and put your hands far out away from your center and see how long you can hold that position, or just put your arms right in line with your shoulders and see how much easier and more efficient that is, just because the bones are aligned more efficiently. So what we see is that these amphibians and reptiles, modern day reptiles as well, they're going to have this sprawled out stance, and their abdomen is also going to be much closer to the substrate. When you compare this to eutherian mammals, and also dinosaurs, by the way, achieved this, what you see is a much more efficient limb anatomy where the limbs are in line with the body, and basically the vector of force of the weight of the animal is where one bone is sitting on top of another bone, giving the animal the most efficiency for standing. Um, Now, also, the swing of the movement of this limb is going to be much more efficient, because instead of having to roll this limb out first and then back in order to step, this is going to work like a hinge, where the limb is just going to be able to swing forwards and backwards just in one unidirectional plane, giving the animal a much more direct movement as it steps. Now, dinosaurs were able to become bipedal, and so were mammals, as humans as being the example. And the reason why this was even possible was because of this bringing the limbs to the center line, which allowed for the animal to actually be able to stand upright and carry its own weight. So here is a picture of that type of efficiency compared, where you see that the salamander on this side has to roll that limb in a circular motion up and around in order to step. And we saw that in the footage. And a dinosaur, even though we cannot see it in real life, we know based on the anatomy that this dinosaur, T-Rex, an example of a bipedal dinosaur, was able to clearly just swing its limbs forwards and backwards in a very similar way as to how humans locomote. When we look at crocodiles and alligators, what we see is a sprawled out posture when resting, but what we see is that in order to gain more efficiency of movement, their limbs actually do come in and move towards the center line, so that they can be more efficient in the movement. So when you look at this picture on the right, you see these dinosaurs here resting with a sprawled out classic reptilian appearance. But then on the left, this frightening photo on this side, what you see is that the limbs have clearly moved to the middle, and this, of course, is going to give that that crocodile a much more efficient gait and efficiency of movement. So here we want to look at the footage of this alligator that is bringing its limbs more medial to its body as it moves, compared to that one over there in the back that's just resting with that sprawled out posture. And so this ability to switch the stance from rest to movement is clearly an adaptation that this reptile has been able to figure out how to use to its advantage. We're going to look at the characteristics and examples of how these limbs change morphologically depending on the different animal that we're looking at. So there are these three classes of ways to make contact with the ground or the substrate. So one is the plantigrade way of doing it, which you as a human are familiar with because you are plantigrade. And that's where the entire foot basically makes contact with the ground, right? So all the way from, let's say, your heel to your toes, you're making contact with the ground. However, that's not the only way of doing it. When you look at a cat, you realize that the foot looks quite different, or the paw, I should say. And the reason why is because they are digitigrade, which means that their digits are making contact with the substrate. They are basically, if you want to think about it from your perspective, when you stand on the ball of your foot, right, and you lift your heel up, then that would be what a digitigrade posture would be like. And the third way of doing it, which we've alluded to already when we talked about our ungulates, is the unguligrade way of doing it, which is where just the tip of the digit makes contact with the ground. And so think about why these variations even exist. And what you notice in this picture is that we are gaining length as we lift more of the manus or the pes off the substrate. We are gaining length of the limb, which, of course, stride length is a big deal for speed. And so think about speed of different animals that you know of and their manus and their pes anatomy and how they place it onto the substrate and how that relates to the speed of their locomotion. So let's look at some plantigrades first. Your plantigrade examples are your humans, your rodents. So squirrels, for example, are plantigrade. Bears are plantigrade. This is a picture of a bear with that plantigrade posture. Raccoons, opossums. And what we see here is that a larger surface area is what's going to make contact with the substrate, creating more stability and being able to carry greater weights for that animal. When we look at digitigrade animals, we see examples are cats, birds, dogs. These are digitigrade animals. And notice that here is an example of a big cat with only the digits making contact right there with the substrate. And so what we're gaining here is speed. And so speed is gained as you go to your digits. Now, there have been a lot of different theories on how humans should run, for example. Now, when we walk, we clearly are plantigrade. However, when we run, and we run fast, if you watch sprinters run, you'll see that they'll be running on the ball of their foot, meaning that they basically turn into digitigrade animals when trying to run at fast speeds. So the cheetah, being the most famous fast animal, accelerating to speeds of 100 kilometers per hour. And what the cheetah is able to do is extreme flexion, which you can see here in this picture, extreme flexion of those limbs, and then extreme hyperextension as it reaches out. So not only are the limbs swinging quickly, but the limbs are actually getting much closer to each other and flexing more and extending more. In fact, that's actually the more important way that the cheetah gains speed, is through this extreme hyperflexion and hyperextension. Here we want to look at how a famous digitigrade predator is going to be chasing after this unguligrade prey. And so both these animals are built for speed, but one is a predator, which means it could not lose all of its digits because it has to be able to claw into the prey. And the prey, on the other hand, being an herbivore, does not need to keep its digits for clawing, and so basically loses all its digits except for one and gains more speed that way. And so evolutionarily, what we see is this race, this arms race for who can be faster, the prey or the predator. So here are some differences between a lizard limb structure and a horse limb structure. Lizard not built for speed, horse definitely built for speed. And what you see is that the musculature of the horse is way up high on the limb, and that the musculature definitely thins out as we uh, make our way down the limb. Now, the reason for this is because we want to decrease the weight of the limb down here, and we want to increase the power of the movement as this limb swings up at the attachment to the girdle. And so again, this is how ungulates get their speed, is that first of all, they get rid of digits, as we've seen over and over again. And they also make sure that their musculature stays way up high in order to decrease the weight down low. When you look at a lizard musculature, what you see is the musculature being strong up close to the point of attachment, but also quite fleshy and bulky down there at the bottom of the limb. Remember, we're going to have a sprawled out posture. We're not swinging these limbs as efficiently. We're not moving as fast as if we are a lizard. And so the musculature anatomy is also going to be different, and that's going to mirror the skeletal anatomy. Here in this video, we want to see how a horse runs and try to make out the upper limbs and the lower limbs and the anatomies and see where the girdles begin. See if you can point out the femur and the humerus. And so if you know what those are, try to see which joint is the elbow joint, which joint is the knee joint. And so then further down, see if you can make out which one would be the wrist and which one would be the ankle joint. And then further down, pay attention to the manus and the pes to see how they are working. So clearly this animal built for running. We talked about the musculature being very, very bulky and thick. closer to the girdle, closer to the point of attachment. And you can really see how this animal can swing its limbs very efficiently. The limbs are right under its body. Um, and that the musculature lightens up as we make our way to the very extremity of the limb, because we want a very light extremity so we can swing it very easily forwards and backwards. Now, the horse will not be as fast as the cheetah, because if you remember the previous video of the cheetah, you saw that incredible hyper flexion, hyper extension, and the horse is just not able to gain that much flexion or extension as the cheetah will. So the horse being very fast, the cheetah will outrun the horse. However, the cheetah does end up getting tired much faster than the prey animals that it tries to outrun. So the prey does have an advantage in the sense that if it can see the cheetah approach and start running uh, early enough, the cheetah will run out of gas and slow down due to burning way too much fuel in order to do what it does. So here we want to look at the gait of a horse and how that gait changes depending on the speed that the horse is trying to achieve. So the limbs are labeled in these different colors: white, pink, black, and blue. This is the walk. And you can see that in the walk, you have a 4-beat gait. And so try to pay attention to when contact is being made by the limb onto the substrate. Each hoof lands on the ground at a different time. And so that's why we call it a 4-beat gait. So it'll be in sequence 1, 2, 3, 4, and that would be the cycle. Once all 4 limbs have touched the substrate, then we are finished with that cycle. So in order to speed up, the next thing the horse wants to be able to do is to change its gait to the trot. And so let's take a look at the trot and see if you can figure out how it changes. How many beats do we see in the trot? Here we have a 2-beat gait, and you can see that the 2 pinks that are diagonal to each other are moving together and hitting the substrate simultaneously, and the 2 black limbs are also diagonal and moving together and touching the substrate simultaneously. And so notice how the horse does change the gait as it changes the speed that it's trying to achieve. Now, the next one is known as the canter or the lope, and this is not quite a gallop yet, but it's getting close to a gallop. And so here we want to go faster. Let's see how this changes. So see if you can figure it out. Again, we have 2 pinks, a blue and a white. So first the blue, then the diagonal 2 pinks touch, and then the white. So this is a 3-beat gait. And a gallop is just a faster canter. So when the horse decides to gallop, it'll just be doing this at a faster rate than during the canter. What is fascinating about this is that we did not know that this is how horses change their speeds until video cameras were invented and we could slow it down. Because if you think about it, have you ever been able to tell how a horse changes its footfalls depending on its speed? And in fact, this was quite a big discovery. Once video cameras were invented, we could really figure out how all the faster animals were able to basically locomote by slowing down and checking to see when the limbs So here what we want to do is analyze how the cheetah gains speed. So let's compare this movement to the horse. And so here in the first phase, what you see, and I've slowed this video down even more than what you find on YouTube, so you may want to do the same thing, is that here what we see is that the lower limbs are pushing off to phase 2 and pushing off the substrate. And now in phase 3, what we see is that we are starting to extend the body. So the lower limbs have pushed off the ground and we're starting to suspend. And now we're in full hyper extension and suspended. Okay, and so this is phase 4. And now what's going to happen is, which is interesting, is that now the upper limbs, or the forelimbs, I should say, touch the substrate. And this is phase 5. And so we're no longer suspended, but now we've switched to propelling the vertebrate forward with the forelimbs. Now the forelimbs are going to push off the substrate. And again, what we're going to see is a suspension phase coming up. But now the suspension phase, and I've paused it here, is in hyperflexion. And so basically what you have are these two suspension periods where no limbs are touching the substrate, and there are two of them for every one that the horse is going to have. And this is how the cheetah achieves speed, is not only via hyperextension, hyperflexion, but achieving two suspension phases where no limbs are touching the substrate for every one suspension phase of the horse. So let's watch this again. We start with 1, the hind limbs pushing off to 2, going to 3, starting to extend, and going to our first suspension, which is hyperextension, and then forelimbs start touching to 5, forelimbs at 6 push off the substrate, going to 7, beginning our flexion, going to our second suspension at 8, and we started over again with 1 with the hind limbs again. Here we want to compare the cheetah's gait to that of the horse. And what we want to point out is, first of all, how extended the cheetah is and how flexed it gets versus the horse, which does not seem to get that extreme flexion and extension. The second thing to notice here, if you look at how much suspension you get, notice here there's a suspension phase that is an extended suspension phase, a flexed suspension phase, and back to another suspension phase. In the same sort of comparison of time for the horse, what you see is that the suspension phase is much more limited in the horse. And so anytime that you're in the air, you're clearly going to be going faster, and you don't have the friction of your limbs hitting the substrate. The other thing we want to do in this table down here is look at the speed of these different fast animals and compare them. So we want to look at, for example, the horse, and we can use miles per hour since we're probably more comfortable with that, at 42 miles per hour, it being the heaviest on this chart, so 540 kilograms. The lion being faster than the horse, lighter. The pronghorn being faster than the lion and lighter. Notice the cheetah, that's the fastest, at 63 miles per hour. Pretty incredible. And its weight being quite light. So the cheetah is a very lightly built cat, actually. And it needs to be lightly built because you cannot have a large mass and move fast. So we decrease the weight, we increase the speed this way. And lastly, we want to look at the human and notice that the human is quite a slow animal. So humans are quite slow compared to these other animals. And actually, we are, when we look at our hunters and gatherers, what we notice is that we are good endurance runners, and we tend to slow down the prey animal that we're chasing. It may take us several hours in order to finally slow down the animal to exhaustion before we go in and kill it for our meal. So humans, in when we look at the family tree of primates, what we notice is that primates came about 40 million years ago. And what we see with primates are that they have forward-facing eyes. They are arboreal organisms, meaning that they live in trees and they are able to move via brachiation or grabbing the branches and swinging. And so these types of primates also, what we notice is that they're good at seeing. Their vision is very good. Um, and that's kind of where we start the story. Now, we do end up getting splits that take place over time. We're not going to talk about all of these, but you can see that the apes do start splitting. And so, what's the difference between an ape and a monkey is that the apes, uh, the first thing you can notice is that there is no tail. And so, apes do not have tails. Orangutans are apes, gorillas, chimpanzees. But you can see where these splits took place with the apes, especially the modern day apes that we're more familiar with. Those splits took place much more recently. So brachiation is the way that these primates move, and this is one of the reasons why our hand is the way it is in modern humans, is that these hands with these opposable thumbs are able to wrap themselves around these limbs. Now, in modern times, we use our hands for tool use, right? Grabbing a shovel, for example, or a broomstick, or holding your luggage, right? But we still use those thumbs in opposition um, in order to do what we do even in modern times. Now, what we notice with the primates that are arboreal and are still moving with brachiation is that their lower limbs are aligned in a way to where the femurs are in parallel, moving straight down. And this is not great for standing on two legs because it does not bring the weight into the midline as well. So what we notice with the in the fossil record, when we look for species that might be the closer relatives of humans, what we look for, one of the things we look for is the articulation of the femur with the acetabulum having this V-shaped structure so that the weight falls right into the middle of that because that is a much more efficient way of standing on two legs. And of course, this is the Australopithecus afarensis fossil, very, very similar structure to what we see in modern humans with that V shape. So when we compare a human to a gorilla, we notice a lot of similarities first off. We do see a much larger pelvis in these other primates and apes, and we need to lighten this skeleton, especially if we're going to be standing on these two legs, we need to lighten it. And so what we see is this much more reduced pelvis. We see that the femurs do have that V shape in the humans. They're kind of bowed out and not as efficient for walking on two legs in the gorilla. When we look at the skull, what we notice is that the nose and the mouth protrudes significantly in these cousins of ours, and in humans, we see that it's much flatter. We see that above the eyes, the where the eyebrows would be is much more prominent in the gorilla and in other apes, and that the brain case is much more reduced compared to the human. You can just see how big that brain case is for the large brain that humans have. Now, when we look at the foramen magnum of different organisms, we see that for a dog, for example, the foramen magnum points, instead of down, points more out to the back, and that's because a dog is a quadruped. And when we look at a chimpanzee, which is not quite bipedal, can stand on two legs, but prefers not to most of the time, the foramen magnum starts to shift more underneath the skull. And then the shift is even more significant in a human, of course, because we are bipedal, so that foramen magnum shifts much more so right under us, because out of the foramen magnum comes the spinal cord, which means the vertebrae would be moving straight down from there. When we look at the hands of a monkey hand, let's say, versus a human hand, we see that they are very, very similar, right? We see this opposable thumb there and in the human, and this is, of course, for the grip from this arboreal lifestyle that we originate from. However, we see that there is a big change that takes place in the pes, because in arboreal organisms, you do see this opposable first digit there for grasping. And so that is the foot of a monkey that still has this big gap between the first digit and the second. You can also see it in this gorilla skeleton right here, that V shape right there. That allows for opposition, a lot of mobility of the thumb there. So move your thumb about in a big circle and see how much movement you get there, and try to do that with your big toe. You see that with the big toe, we have lost that ability. And that's because now we are cursorial. We are walking. We are no longer swinging from one branch to the other. And so we've lost the ability to do that with our feet. Now, the reason why we've kept that ability with our hands is, of course, because we've become tool use bipedal organisms. So our hands have still maintained that anatomy because it is still useful for us today, right? Whether we are trying to hunt with a spear, okay, or whether we're playing the guitar, you'll see that the opposable thumb is still necessary today. Now, in terms of where these hominids or human-like ancestors came about, well, we have found through the fossil record that these hominids came about from Africa. So Africa is the point of origin for the human ancestor line. And we're not going to go over all of these, but for example, Ardipithecus is going to have that skeleton with the smaller pelvis and the V-shaped femurs around 5 million years ago. And that tells us that this animal right here was definitely on two legs, bipedal, still with the lower limbs looking like they were there for grasping. So we're not completely human yet. We're kind of an in-between arboreal and cursorial animal. We're still holding on to the older structures and starting to gain some of the more modern structures. Now, these early hominids were smaller than modern-day humans, so you'll typically see this 4-foot tall kind of number that you see over and over again. Later on, we get to Lucy about 3.5 million years ago, and this was the Australopithecus line. She also was a small hominid structurally. So these are not as large as modern day hominids. Later on, and we're going to see this in a few slides, we get to Homo erectus, some of the more famous types, Homo neanderthalis, and even smaller ones, Homo floresiensis, which is like the hobbits that have been found as well in the Asian Pacific Islands. So here are some comparisons. For example, when you look at the chimpanzee and you see that big pelvis, right, and you see that bowed out femur structure, and you compare that to Lucy with a much more delicate pelvis, made for walking upright, the femurs having that classic V-shaped, the skull definitely getting larger, which means we can imagine a situation where these animals were getting more intelligent. And still small in stature. So remember that we're talking about, 4 feet tall in height, compared to the modern human, a taller, more elongated and delicate skeleton as we get to the modern human. The skulls give us an idea of how the brains changed and how the strength of the jaw changed. So in general, the skull became more delicate as we approach humans, and the brain case became larger. So you can look at, for example, the Homo sapiens skull here and notice how much larger that brain is compared to, for example, the Lucy skull. However, surprisingly, Neanderthals had larger brain cases than humans. And so the question of brain size and intelligence is something that has been argued about quite a bit. Is the brain size the only thing that is determinant of what the intelligence is? And if so, what does that say about the intelligence of Neanderthals versus modern day Homo sapiens? It's probably more complicated than just brain size. There's probably other factors as well. So Homo erectus, you can see quite a big brain case, but also a very, very powerful looking jaw, meaning that this species was definitely eating much tougher foods than the more modern day hominids. And so what we see as a general trend is that the brain case is getting larger. And what this graph is nice about, is that if you take the Homo sapien, it shows you how recently we came about, right? This is the timeline right here. So we're about 200,000 years old, and that we also were around at the same time that Neanderthals came about. It's clear now through DNA analyses that a lot of humans have Neanderthal DNA inside of them. Any European, for example, has some Neanderthal DNA inside of them, which means that there was some interbreeding between these two species. What kind of interactions they had is a big question mark. Did they get along? Did they go to war with each other? Was the Homo sapien responsible for the extinction of the Neanderthal? These are questions that we're still asking. Homo erectus also concurrent at some points with these others. And more information is coming out. So even as I'm lecturing on this, this graph may be slightly out of date as we get more information. And then typically every few months we find another fossil that revises this story a little bit for us. But it's clear that at some point there were several different human-like species roaming about the earth simultaneously, and what their interactions were like is obviously speculation. So side by side with the Neanderthal, remember that Neanderthals really had colonized Europe quite a bit and kind of held that ground and were kind of the gatekeepers to Europe for thousands of years. And in fact, there is some evidence that Homo sapiens had tried from Africa to infiltrate Europe on a couple of different occasions, and were probably held back by the Neanderthals successfully for at least some time until eventually the Homo sapiens did break through. You can see that the Neanderthals were a bit stouter in stature, a bit stouter and tougher and bulkier in terms of their anatomy. Homo sapiens did end up thinning out their skeleton, so we do see this slendering of the skeleton, this lightness of the skeleton compared to the Neanderthals, and basically this typically has to do with lifestyle in terms of what they were doing and how much activity, how much physical activity was necessary for them. It could have been that certain technologies of humans allowed for them to get away with a more delicate anatomy. We obviously do see that the jaw bones and the musculature around the skull did decrease as we approach more human time periods. Notice also a characteristic of Neanderthals is this rib cage that does flare out, and they've done some theoretical experiments to try to figure out what kind of sounds Neanderthals would have made based on their anatomy, and the rib cage was one thing that they did refer to. Now, the depictions of Neanderthals has changed over time, and so this is kind of like an older way of depicting them, very cave man-like, very primitive looking. And that story is changing, interestingly enough, to something that looks more like this, where the Neanderthals look much more human in modern day depictions compared to the ones that were being drawn a few decades ago, to the point where some would say and argue that if you saw a Neanderthal walking down the street, you may not even think too much about it, and might just think that's just just a human. So how different they were from us is clearly speculative, and as we keep finding more about their civilizations through what they left behind, what kind of tools they were using, what kind of animals they were eating, did they have art, did they have any language, all that stuff, more information will come out over time, hopefully, so we can try to clear up some of these burning questions.